Welcome to this lecture. This is the final lecture of week 2. So, in this lecture we are going to discuss some interesting problems involving the material that we have covered in week 2. Recall that in this week we have discussed about product measures, Fubini's theorem and independence of events and random variables. So, without further delay, let us move on to the slides and discuss certain interesting problems. We start with the discussion on proposition 1. So, just to recall, what we have seen there earlier was that for any non-negative random variable x, the expected value, which always exists in the sense that this quantity takes value between 0 and infinity, infinity included as a possible value, that quantity can be represented in terms of the integration over the tail probability, alright. So, this kind of a formula we had shown as an application of the Fubini's theorem. Now, more generally, what we had applied this result to was that fact that expected value of mod of x, here mod of x is non-negative and that has a certain again integral representation. So, we had used that to again obtain certain nice convergence properties for certain series and all that. But now we are interested to talk about general random variables and expected value of itself. So, let us see. So, if you work with a general random variable x, then when we talk about the expected value, we are going to look at the expected value of x plus and expected value of x minus. Recall what are these random variables x plus and x minus? So, x plus is a random variable defined as the maximum between x and 0. And x minus is defined as the maximum between minus x and 0. So, if you look at that, then it is a immediate fact that x can be written as x plus minus x minus, and moreover mod of x has this formula that it is x plus plus x minus. So, with this in the background, when we talk about expected value of x, we would like to make sense of this difference. When this difference makes sense, then we say the integral of x, which is expected value of x, exists. So, here note that if both these quantities expected value of x plus and expected value of x minus, if both of these are finite, then there is no problem in looking at the difference. But if one of them is finite and the other is infinite, then the difference can take value plus or minus infinity, which we now allow. But if both of them turn out to be infinity, then we end up with this infinity minus infinity situation, in which case we cannot make sense of the integration. In these cases, we say that the expectation does not exist. When we consider the situation when this difference makes sense, that is including the case when at most one of them is infinity. So, then we can talk about this expected value as this difference, but now both x plus and x minus are non-negative random variables for which our earlier proposition applies. And there we can write this integration involving the tail of x plus and x minus. But here you note that when we are varying this number small x on 0 to infinity, here x plus being greater than x means that the value of x itself must be positive, and as a consequence x minus must take the value 0. So, when we are talking about the event x plus being greater than x, that is exactly the same as the event together with x minus being identically 0 on that event. So, these events are same. So, that is what we write in terms of this formulation. Similarly, when x minus is greater than this number small x, then again we can say that the positive part of x, which is x plus, must be again 0 on this event. So, that is why we rewrite using this formulation involving both the components x plus and x minus. But now, when these both components values are clear to us, what we can do is that we can rewrite in terms of the original random variable capital X. On the first case, we are working with x in 0 to infinity and x plus greater than x and x minus identically 0. So, here the random variable x, which is x plus minus x minus, is taking the values of x plus and therefore this is greater than x. So, that is what we have rewritten here. Again, when x minus is positive and x plus is identically 0, in that case the original random variable is taking negative values and values will be less than of minus x. So, that is why expected value of x for a general random variable has this expression in terms of difference of these two integrals. Moreover, note that this final integration that we have seen here can be further simplified and written in other formulations, like we can change variables from minus x to say y, then y will vary from minus infinity to 0 and we will be talking about x probability of x less than y dy. So, that formulation we can also apply by changing variables here with appropriate signs introduced in front of the integration. So, therefore, expected value of x can be rewritten in these different forms by an application of the proposition 1 which we have seen earlier. This is again an application of the Fubini's theorem. Alright, so let us move on. Now, we go look at certain interesting properties of the distribution function of a random variable. Remember that given any random variable x defined on some probability space omega fp, the distribution function is given by this formulation, and that we know in terms of our usual notation that probability of capital X less equal to small x. Now, here we are varying small x over the whole of the real line. Now, if you fix any constant c positive, then the distribution function, as we know, it is a non-decreasing function. Therefore, this difference of the function values must be positive, because c is positive and therefore x plus c must be greater than x. So, using the non-decreasing property of this distribution function, we end up with this inequality pointwise for all x, and hence what we can conclude is that this is a non-negative function. If we integrate with respect to the Lebesgue measure, then over the real line the full integration will also be non-negative. Now, here we have hidden the Lebesgue measure using our usual notational convention, but underlying the integration has to be done through the Lebesgue measure. Now, we note that we can actually compute the exact value of this integration as an application of again Fubini's theorem. What do you do is that we start with this expression which we want to compute. Now, here we go back to the definition of the distribution function, and there what we observe is that this difference can be written as the probability of this event, that the random variable takes values between two ranges x and x plus c, x excluded and x plus c included. Alright. So, that is the range of probability that we need to consider. But here this probability can be rewritten in terms of an additional integration over the omega variable with respect to the underlying probability measure, and to do that what we need to do is to look at this indicator function. Now, here what we have to just check is whether the values of the random variable are inside this interval small x to x plus c, small x excluded. Now, if that happens, we will write the value 1, otherwise we will take the value 0. So, that is connected to this integrator function, and therefore, we have written this probability in terms of this additional integration. But note that the indicator function that we are using, that is taking values 0 or 1, in particular it is non-negative. So, there we can appeal to the Fubini's theorem and go for the exchange of the order of integrations. So, what we do first is we perform the Lebesgue integration first and then perform the improbability integration. Now, what happens to the Lebesgue integration? Let us see. So, here for simplification what we do is that we write this Lebesgue integration's integrand as a function involving the variable small x. Then this indicator function can be rewritten as this, that the small x should be taking values in this interval, and that is the indicator that we need to look at. So, if you now look at the integration with respect to the Lebesgue measure first, what do we get is that we get the length of the interval with respect to the Lebesgue measure, and then we have to integrate that further with respect to the underlying probability. Now, here what happens is that this length is nothing but this constant c, because the points that we are using are x omega minus c to x omega, and therefore, the length of the interval in question is exactly c. And if we integrate this constant c with respect to the probability measure, we end up with the value small c. And therefore, what we have ended up computing is that for any positive number c, the distribution function has this interesting property that the integration of f x plus c minus f x over the whole real line, that actually is exactly equal to this constant small c, and this is true for any positive constant c. Alright. So, let us see some further interesting comments on independence of random variables. Recall from earlier that if x and y are independent random variables on some probability space, then what we can do is that we can apply functions on top of them and obtain new random variables, and we can ask whether these new random variables are independent or not. So, here what we do, we take two Borel measurable functions on the real line and look at the random variables f of x and g of y. Now, here by the measurability of the functions f and g, if you take any Borel sets a and b, then their pre-images must again be Borel subsets of the real line. Now, we go back to verifying the properties of independence for these new random variables f x and g y. Here, probability that f x takes the value inside the set A and g y takes the values inside the set B, that can be simplified in this formulation, that x must take the value in f inverse of A and y must take the value inside the set G inverse of B. So, to clarify this, let us do this simple computation. When we write f x takes the value inside the set A, that simply means this is the subset of the domain set such that f of x of omega takes the values inside the set A. But then you observe that this is nothing but omega such that x of omega must be in f inverse of A, and that is what we simplify using our usual notation that x takes the value inside f inverse of A. So, that is the type of arguments that we have used here to simplify our previous steps expression. Once we have this, we appeal to the given independence of the random variables x and y. So, here what we can do, we can split the probabilities in terms of the individual events involving x and y. But now we go back in the argument and write in terms of the random variables f x and g y, and what we ended up having is that the new random variables f x and g y must be independent of each other. So, as a consequence of this, we can choose some nice Borel measurable functions f and g and obtain new independent random variables. In particular, if you look at the square functions or the cubic functions, and given that x and y are independent, what we will get is that x square and y cube, they are independent of each other. We could have also chosen x square and y square and concluded that they are also independent. More generally, we can extend these arguments to classes of random variables. First, to clarify this structure, what we are looking at are two separate collections of random variables which are given to be independent of each other. Once we have that, we can construct functions which are based on separate such collections. For example, if you take three random variables, let us say x, y and z, and suppose they are mutually independent, what you can look at are two distinct collections of random variables, which is this pair of random variables x and y in one collection and the random variable z in another collection. Now, given the mutual independence, we will immediately have that these two collections are independent of each other. But now what we can do is that we can look at the addition function on the first collection. So, that will give us the new random variable x plus y. Now, what we can conclude from this kind of argument that we have discussed so far is that x plus y and z must be independent of each other. More generally, we can appeal to other interesting such functions, and we can say that let us say x plus y and z square are independent of each other. So, this kind of further reductions can also be obtained, and this kind of independence arguments will be used towards the later side of our course. So, we move on and discuss another interesting property involving independence of events. Recall from earlier that we have discussed two different notions of independence of events. One is mutual independence, another is pairwise independence, and we had commented earlier that in general pairwise independence does not imply mutual independence. Let us see this fact through an example. So, what we do here is that we take this set 1, 2, 3, 4. So, this is the 4 element set, and here what we consider is the power set sigma field. So, this gives us a measurable space. Now, on top of that we consider the probability measure, which is the uniform probability measure. To do that, what we have to do is that since there are 4 distinct elements, to each of these singleton sets we assign the same mass, which is 1 over 4, and this can be extended all subsets of the set omega. Once you extend this, you get other probabilities that you can compute. Now, here what we consider are these 3 specific events, which we denote by A, B and C. So, A we take 1, 4, B we take 2, 4 and C we take 3, 4. Now, here since all of these are 2 element sets, then probability of A, probability of B and probability of C, all of these turn out to be half. Now, note that all of these sets have a common intersection given by the points 4, and therefore, if we try to compute probability of A intersection B, A intersection B is the singleton set 4, and therefore, the probability of that event is exactly 1/4. Similar facts are true for probability of B intersection C and probability of C intersection A. And once you observe this, we immediately conclude that probability of A intersection B, that is same as the product of the probabilities of the events prob A and B, and therefore, the events A and B are independent of each other, that is the pairwise independence. Moreover, this is verified for all these pairs AB, BC and CA. Therefore, this collection ABC are pairwise independent, but we can try to check whether these are mutually independent or not. What we observe is that these 3 sets again have this common element singleton 4, and therefore, the full intersection is the singleton 4 and the probability of that is exactly 1/4. But that does not match with the product of the probabilities of these individual events, which turn out to be 1/8. Therefore, these events A, B, C are not mutually independent. So, this shows by example that pairwise independence may not imply mutual independence. Of course, what we have seen earlier is that mutual independence is a stronger condition than pairwise independence. So, mutual independence always implies pairwise independence, but the converse may not be true. Alright. So, now we go back to another interesting application of the Fubini's theorem in terms of the volume of the unit ball that we have seen earlier in remark 4. So, here what we see is that if we denote the volume of the unit ball in n dimensions as alpha n, then we had discussed this recurrence relation given by this formula, that alpha n is 2 pi over n times alpha n minus 2. Now, using these recurrence relations for large n, what we observe is that this ratio alpha n by alpha n minus 2, which is exactly 2 pi over n, that can be made small and smaller than half, say. So, to do that, all you have to do is to choose n larger than 4 pi. If we do that, then you immediately have this bound which is less than 1. Now, as a consequence of that, if you let n go to infinity over even integers, then what happens is that these alpha n's must go to 0. Here note that we are taking only even integers and using the fact that if n is even, n minus 2 is also even, and then this ratio will give us that this limit must go to 0. Again, if you are considering odd numbers n and let it go to infinity, then we first observe that n and n minus 2 both are now odd numbers, and then again we appeal to this ratio, and therefore, for large n these alpha n's must be small, and as a consequence of that limit of alpha n's must be 0. Now, separately if we take limits over the odd n's and even n's, both turn out to be 0, and therefore, as a consequence what we conclude is that the original sequence, no matter n is odd or even, that sequence must converge to 0. So, what it gives us is some kind of a counterintuitive result, that the volume of the n dimensional unit ball that goes to 0 as n increases. So, in this discussion we have seen some applications of Fubini's theorem and other related interesting comments on independence of random variables and events. I suggest that you work out the exercises that has been left out and discuss further in the Google Group forums. Thank you.